Hello and welcome to another video of my Capstone project. Today we're going over the first part of electrochemistry, and this first part will be focused on what's called a redox reaction. This consists of two things. We have reduction and we have oxidation. And when you combine those two words, you get redox. Now reduction and oxidation, they stand for the transfer of electrons. So reduction, that's going to be our gaining of electrons. And our oxidation is going to be the loss of electrons. And in any redox reaction, both of these happen at the same time. For example, if you were to give your friend some money, someone is always going to be giving money and one's always going to be receiving money. You can't have someone giving money but no one receiving the money. So similarly, you have to gain electrons and lose electrons at the same time in a redox reaction. So you'll always have reduction and oxidation at the same time. Despite this, we'll be breaking down full redox reactions into half reactions, which can be used for balancing and simplifying things. For example, if we have this equation, 2Na plus Cl2 forming 2NaCl, there are two half reactions going on, one oxidation and one reduction. Our oxidation one is our sodium atom turning into its ion, sodium plus, and the charge went up by 1, so it lost an electron. You took away a -1 charge, and that became a +1 charge. And then we have our chlorine atom, and this time it's going to gain 2 electrons because it's going to turn into our 2Cl-. And you can really look at this intuitively if you just look at the charge and know that an electron is -1. In our first half reaction here, we can see that Na lost an electron, so that's going to be oxidation. And for chlorine, it gained electrons, so that's reduction. Now let's look at what oxidizing and reducing agents are. So an oxidizing agent, or OA for short, that's going to be the thing that reduces. And on the other hand, our reducing agent, it's going to be the one that oxidizes. So looking at this example, we know that our sodium oxidized, so that's going to be our reducing agent because it causes reduction. That's why it's the reducing agent. But the reducing agent itself will oxidize. And our chlorine, it reduced, so that's going to be our oxidizing agent. Now let's determine the spontaneity of redox reactions. First thing we do is we look at our standard reduction potentials table and we identify all our oxidizing and reducing agents. Specifically, we're looking for the strongest oxidizing agent and the strongest reducing agent. And look at the chart, you see on the left hand side, going up the table, the oxidizing agents get stronger. And on the right side, they get weaker as you go up and stronger when we go down in terms of reducing agents. And for this example here, let's look for our oxidizing agents and reducing agents. So first we have to identify what's happening here. So like what gets reduced and what gets oxidized. The first thing I see is that our magnesium here, which is originally neutral, becomes magnesium 2+. So it gained, so the charge went up. It went from 0 to +2. And from that, I know that our magnesium, it lost 2 electrons. And that's why the charge went up by 2. For our Cu here, it went from +2 to neutral. That means it gained electrons. And because it's gaining electrons, that's going to be reduction. And our magnesium is going under oxidation. Now let's label our reducing and oxidizing agents. We know that magnesium is oxidizing, so that's going to be our reducing agent. And our copper, it reduces, so it's going to be our oxidizing agent. And then similar to our acid and base unit, you kind of treat these as like conjugates. So if on the left side it's going to be the reducing agent, on the right side it's going to be the oxidizing agent. Same for copper. Now we want to find the strongest reducing and oxidizing agent. So we use our chart. We can see that magnesium, it's going to be a strong reducing agent. And for copper 2+, that's going to be our strongest oxidizing agent. And again, similar to acid and bases, a strong reducing agent is going to turn into a weak oxidizing agent. And a strong oxidizing agent is going to turn into a weak reducing agent. If you look at the chart. Now, how do we determine the spontaneity of this equation? We look at our two strongest reducing and oxidizing agents, and we're going to see if they are downhill from each other on our table. And what that means is, if you take your strongest reducing agent and you draw a line, a straight line from there to your strongest oxidizing agent, going from left to right, it should go downhill. I'll post a picture of the chart right here. And as you can see, it is downhill. And they are downhill from each other. So this is going to be spontaneous. If they were uphill, then it would be non-spontaneous, meaning you'd have to put in energy for it to proceed. Now, before we start constructing full redox reactions, we have to construct half reactions. Sometimes you'll need to find a half reaction that's not on this table, and you have to construct it yourself. And when constructing these, you have two scenarios. It could either be in an acidic solution, or it could be in a basic solution. I'm going to look at both of these. Start with acidic. Let's write a balanced half reaction for N2O4 turning into NO3- in an acidic solution. And we're going to use what's called the major OH- method. So write it out. Major OH and minus. And we're just going to go down this list. Major stands for any major species that's not hydrogen or oxygen. And we can see that nitrogen here is a major species. And we're going to balance that first. So we're going to write our new equation here with our nitrogens balanced. So a coefficient of 2. And now our nitrogens are balanced. Next, we have O. That stands for oxygen. We're going to balance the oxygens by adding water. And we see we have 4 oxygens on the left side and 6 on the right side. So we have to add 2 to the left side. We're going to add 2 waters. And now we see that our oxygens are balanced. We have 6 on the left side and 6 on the right side. Next, we're going to balance our H, which is our hydrogen. And we do this by adding H+. We see we have 4 hydrogens on our left side and none on the right side. So we're going to add 4 H+ to the right side. It's going to look like N2O4 plus 2H2O. It's going to turn to 2NO3- plus 4H+. Okay, we're almost done. Now for the minus, we're going to add electrons to balance the charge of both sides. Looking at the left side, we have two neutral species. They're both neutral, N2O4 and water. But on the right side, we have NO3 minus and H plus. Our NO3 minus, that contributes to -1, and we have two of them, so that's going to be -2. So that's going to be -2. Our H plus, that's +1, and we have 4, so that's going to be +4. So adding it up on our right side, we have a charge of +2. And we need to somehow make that equal to our charge on the left side, which is 0. And how do we make +2 into 0? We minus 2 by adding 2 electrons. So it's going to look like this. And now we're done. And we can check to make sure both sides are balanced by adding up the total number of each species and then also the charges. And that's in an acidic solution. But what if it were in a basic solution? Here's what we do. So we do the exact same thing as if it were an acidic solution, so what we just did. But at the very end, we're going to neutralize all our H plus by adding an OH minus to both sides. So let's say we were doing the exact same problem, except it was basic solution. So at the end here, we're going to add 4 OH minus to both sides, because we have 4 H plus to neutralize. And these two, they will neutralize and form 4 waters. Now we can rewrite our equation. N2O4 plus 2H2O plus our 4 OH minus, forming 2 NO3 minus plus 4 H2O and 2 electrons. Finally, we can cancel out our 2 waters on our left side and our waters on our right side. And that is our finished half reaction. Now that we know how to balance half reactions, we can move on to balancing full reactions. And balancing full redox reactions, we have 2 methods. One is called the half reaction method, and one is called the oxidation number method. We'll start by looking at the half reaction method. Let's say we want to balance the full redox reaction of Na plus Cl2 going into Na plus and Cl minus. First, we have to check the spontaneity of this. We know that Na is our strongest reducing agent, Cl2 is our strongest oxidizing agent, and looking at our chart, we can see it's downhill, so it is spontaneous. So we can move on to step 2. We're going to write down both the reduction and oxidation half reactions. And how we do this is we look at our table and we find these 2 agents here. Otherwise, we'll have to construct our own half reaction like we did earlier. So let's look for the 2 half reactions. For our reduction, we have Cl2 plus 2 electrons to turn into 2 Cl minus. And for our oxidation, we have Na turning into Na plus and an electron. For our second equation, so our oxidation half reaction, you have to remember to flip the equation, because know that this chart, if you look at the top, it says standard reduction potentials of half cells. So these are all reduction half reactions. So you have to flip the equation to get your oxidation one. Okay, next we're gonna try to balance the number of electrons by multiplying the entire half reaction. We see that in our reduction we have 2 electrons being gained, and in our oxidation we have one electron being lost. So we have to multiply the entire oxidation reaction by 2 so that our electrons can cancel out. So we'll have 2 NAs becoming 2 Na plus and 2 electrons. Now we can just cancel out the electrons. So boom and boom, it's gone. And now we add the reactants together and then the products. And now if you don't have anything else to simplify, then you're done. And that's the half reaction method. Next is the oxidation number method. And before we can do that, we have to learn what oxidation numbers are. What it is, it's kind of like an imaginary charge if we pretended that some particles were actually ions. So it's an imaginary number, but it's going to be important. Let's look at some common oxidation numbers. So if you have any element by itself, for example, just Na by itself, or just a Cl by itself, or even a Cl2, these all have oxidation numbers of 0. Or you could say they are neutral. If you have a hydrogen in a compound, so hydrogen in a compound, such as HCl, hydrogen is going to have a +1 oxidation number. Though sometimes in hydrides you'll have a -1 for hydrogen, but that's really rare, so don't worry about it. Next is oxygen in a compound, such as H2O, and they will have an oxidation number of -2. Unless it's in a peroxide or an oxide. For example, hydrogen peroxide, our oxygen is going to be -1. But that's just an exception. It's kind of rare. And finally, for any monoatomic ions, so ions, it's just going to be the charge. So our Na plus is going to be 1, Cl minus is going to be -1, S2 minus is going to be -2. So pretty simple, determining the oxidation number of things. Now let's look at an example. We're going to try to find the oxidation number of Cr in Cr2O7 2-. Now we don't know what the oxidation number of Cr is, so we have to look at what we do know. We know that this entire molecule has a charge of 2-. And we know that our oxidation number for oxygen is going to be -2. I'm going to put it in red. -2. And then, because we have 7 of them, that's going to turn into -14. And now, we know that our Cl2 has to make up something that will turn this -14 into a -2. What that means is, if you pretend that it's like a charge, let's say your oxygen, it contributes to a charge of -14, and you want to add something to it to turn it into -2. Well, you have to add to -14 to make -2. You have to add 12. So your Cr2 oxidation number will be 12, and since you have 2 of them, your Cr is going to be 6. And that's your answer, +6. Basically, you're just adding and subtracting numbers to make it equal to the charge of the entire compound. Let's look at another example. NaClO4, and we want to find our Cl oxidation number. We start with what we do know. We know that our oxygen is -2. That's going to contribute to -8. And we know that Na plus, that's going to be +1 too. So we'll put +1 down here. And what we can do is down here, right? We can make this equal to the charge of the entire compound. So the charge is going to be 0. So we have 1 plus something minus 8 is equal to 0. So we know it's 7. So Cl oxidation number is 7, or +7. Now we can do the oxidation number method. Okay, here are the steps to this method. And we're going to try our example of H2S plus NO3 minus becoming NO plus S. And this is in an acidic solution. First, we need to write out all the oxidation numbers. We know that H is going to be +1. That contributes to +2 because you have 2 of them. So our S must be -2 because the whole thing is neutral. So -2. For NO3 minus, our oxygen is -2. We have 3, so that's -6. The entire charge of the molecule is -1. So something -6 is -1. That's going to be 5. For NO, O is -2. The whole thing is neutral, so N has to be +2. And S is just an element, so that's 0. Now we find out what went up and what went down in terms of oxidation numbers. Let's start by looking at S. Our S went from -2 to 0. And we know that that's a loss of electrons. So we're going to go and connect them. And we're going to say this is going to be oxidation. And -2 electrons. Next, we can see that our nitrogen went from 5 to 2. We're going to connect them. So it went down by 3, right? So you gained 3 electrons. That's reduction. So now we multiply the 2 electron differences so that they equal each other. We know that 3 and 2 have a common multiple of 6. So we multiply top one by 2 and bottom one by 3. And similar to the other method, we're trying to cancel out the electrons. And multiplying by 2, we add that as a coefficient. And same for 3. And finally, we balance our O and our H by adding water and H+. And once you did that, it's going to look like this. And you can check your answer, and you're done. And that's the oxidation number method. And I forgot the charge on NO3. Make sure you include the charge. And I recommend doing lots of practice on balancing these equations, because that's the main thing you'll be doing for the next test. Finally, you have redox titrations. And these are actually really simple because the only new thing is writing out your balanced redox reactions. And by now you should be experts at titrations. So I'm not going to spend much time on this because what you do is you just write out your balanced redox reactions, and just like your acid and bases, you use the coefficients to find your unknown. And that's it. Very simple. Okay, hope that helped. Good luck. Bye-bye.